Understanding the oversubscription of power distribution unit, or PDU, ampacity in a data center environment is crucial for maintaining both efficiency and compliance with the National Electrical Code, or NEC. The NEC provides guidelines that allow for a certain degree of oversubscription, especially in data centers where the maximum demand is not always constant or fully known. Let's explore the relevant NEC requirements, specifically focusing on Article 645.5 D2, which addresses branch circuits supplying data center equipment. This article states that when the maximum demand of a data center is uncertain, Table 645.5 D2 should guide the determination of the minimum number of branch circuits required to supply the total load. The key is to calculate the number of branch circuits needed by multiplying the total load by the demand factor specified in Table 645.5 D2 and then dividing by the branch circuit rating. The demand factor plays a vital role in this calculation, allowing for a reduction in the total calculated load based on the assumption that not all equipment will operate at its maximum capacity simultaneously. Table 645.5 D2 provides specific demand factors for various types of data center equipment, including server racks, network equipment, and storage equipment. For server racks, a common component in many data centers, the demand factor is typically 0.6. This means that only 60% of the total rated load of the server racks needs to be considered when calculating the required branch circuit capacity. Network equipment also often has a demand factor of 0.6, while storage equipment may have a lower demand factor, such as 0.5. To illustrate how these demand factors are applied, let's consider a scenario with a 150 kilovolt-amps PDU. Using the demand factor for server racks, which is 0.6, we can calculate the maximum allowable ampacity of the branch circuits. The calculation is as follows: 150 kilovolt-amps multiplied by 0.6 divided by the voltage. If we assume a 208-volt system, this equates to 430.6 amps. This calculation indicates the maximum ampacity that can be legally drawn from the branch circuits connected to the 150 kilovolt-amps PDU, taking into account the demand factor. Now, let's determine the extent to which the PDU ampacity can be oversubscribed based on this demand factor. To do this, we divide the maximum allowable ampacity, which is 430.6 amps, by the rating of a single branch circuit. If each branch circuit is rated at 30 amps, then the calculation is 430.6 amps divided by 30 amps, which equals 14.35. This result suggests that the PDU ampacity could be oversubscribed by up to 14.35 times the rating of a single 30 amps branch circuit. However, it's essential to consider the physical limitations of the panel board to which these branch circuits are connected. If the panel board has 42 poles available for 30 amps feeds, the theoretical maximum ampacity that could be connected is 42 multiplied by 30 amps, which equals 1260 amps. This is significantly more than the maximum allowable ampacity of 430.6 amps calculated based on the demand factor. The NEC requirements and the demand factor for server racks allow for a specific number of 30 amps feeds to be legally connected to the 150 kilovolt-amps PDU. In this scenario, up to 14 such feeds could be connected. It is important to recognize that this is a maximum allowable oversubscription. While the NEC permits this level of oversubscription under specific conditions, careful management of the actual current capacity of the PDU is paramount. Overloading the PDU can lead to overheating, equipment failure, and potential safety hazards. To ensure safe and reliable operation, continuous monitoring of the current draw on each branch circuit and the overall PDU load is necessary. This can be achieved through the use of intelligent PDU with built-in monitoring capabilities or through external monitoring systems. These systems provide real-time data on current voltage, power consumption, and other critical parameters, allowing data center operators to identify potential overloads and take corrective actions promptly. Moreover, it is crucial to maintain accurate records of the equipment connected to each branch circuit, including their power requirements and operating characteristics. This information is essential for effective capacity planning and load management. Regularly reviewing and updating these records helps ensure that the PDU capacity is not exceeded and that the data center operates within safe and efficient parameters. Furthermore, it is advisable to implement policies and procedures that govern the addition or removal of equipment from the branch circuits. These policies should include a thorough assessment of the impact on the overall PDU load and a verification that the new configuration remains within the allowable limits. Training data center personnel on proper load management techniques and the importance of adhering to the NEC guidelines is also essential. This training should cover topics such as calculating branch circuit loads, monitoring PDU capacity, and identifying potential overload conditions. In addition to the NEC requirements and demand factors, there are other considerations that can influence the design and management of branch circuits in data centers. These include the type of equipment being powered, the redundancy requirements of the data center, and the overall power distribution architecture. For example, if the data center houses equipment with highly variable power demands, such as high-performance computing servers, it may be necessary to use a lower demand factor or to implement more granular monitoring and control capabilities. Similarly, if the data center requires a high level of redundancy, it may be necessary to provide multiple independent power feeds to each rack or equipment, further complicating the branch circuit design. The overall power distribution architecture of the data center also plays a role in determining the optimal branch circuit configuration. Some data centers utilize a centralized power distribution architecture, where power is distributed from a central location to the various racks and equipment. Other data centers employ a distributed power distribution architecture, where power is distributed from multiple locations, providing greater redundancy and flexibility. In either case, the branch circuit design must be carefully coordinated with the overall power distribution architecture to ensure that power is delivered efficiently and reliably to all equipment. In conclusion, understanding the NEC requirements, demand factors, and load management techniques is essential for safely and efficiently oversubscribing PDU ampacity in data centers. By carefully calculating the maximum allowable ampacity, monitoring current draw, and implementing appropriate policies and procedures, data center operators can maximize the utilization of their power infrastructure while minimizing the risk of overloads and equipment failures. This approach not only ensures compliance with the NEC but also contributes to the overall reliability and efficiency of the data center. Remember that electrical codes can change, and it is important to consult with a qualified electrical engineer or inspector to ensure compliance with the latest regulations and best practices. Firstly, NEC Article 645.5 D2 provides guidelines for oversubscribing branch circuits in data centers. Secondly, demand factors from Table 645.5 D2 are used to calculate minimum branch circuits based on equipment type. Thirdly, for server racks, a demand factor of 0.6 is commonly applied. Fourthly, calculate maximum allowable ampacity using the formula 150 kilovolt-amps times 0.6 divided by 200 volts equals 430.6 amps. Fifthly, determine oversubscription by dividing maximum ampacity by branch circuit rating. 430.6 amps divided by 30 amps equals 14.35. Sixthly, consider panel board capacity which may exceed allowable ampacity. Seventhly, legally connect up to 1430 amps feeds based on NEC and demand factors. Eighthly, manage actual current carefully to prevent overloads. Ninthly, monitor current draw continuously via intelligent PDU or external systems. Tenthly, maintain accurate equipment power requirement records for capacity planning. 11thly, implement policies for adding or removing equipment to control load. 12thly, train personnel on load management and NEC compliance. 13thly, consider equipment types such as high-performance computing servers with variable power demands. 14thly, address redundancy requirements by providing multiple power feeds. 15thly, coordinate branch circuit design with power distribution architecture, centralized or distributed. 16thly, consult with electrical engineers or inspectors for current regulations and practices. 17thly, implement a robust monitoring system that provides real-time data on current, voltage, and power consumption for each branch circuit. 18thly, establish clear thresholds and alerts to notify data center operators of potential overload conditions, enabling them to take proactive measures. 19thly, conduct regular audits of the power distribution system to identify any imbalances, inefficiencies, or potential points of failure. 20thly, ensure that all electrical equipment used in the data center is properly grounded and maintained to prevent electrical hazards and ensure reliable operation. 21stly, use appropriately sized conductors for each branch circuit to minimize voltage drop and ensure efficient power delivery. 22ndly, install surge protection devices to protect sensitive electronic equipment from voltage spikes and transients. 23rdly, maintain adequate ventilation and cooling to prevent overheating of electrical components and ensure optimal performance. 24thly, implement a comprehensive emergency power off or EPOR system to quickly shut down power in the event of a critical failure or safety hazard. 25thly, develop and regularly test a disaster recovery plan that includes procedures for restoring power and data center operations in the event of a prolonged outage. 26thly, collaborate with power utility companies to understand grid conditions and potential impacts on data center power supply. 27thly, consider implementing energy efficiency measures such as power factor correction and variable frequency drives to reduce energy consumption and lower operating costs. 28thly, explore the use of renewable energy sources such as solar or wind power to supplement grid power and reduce the data center's carbon footprint. 29thly, participate in industry forums and technical conferences to stay up to date on the latest trends and best practices in data center power management. 30thly, foster a culture of safety and continuous improvement within the data center team to ensure that power management practices are constantly evolving to meet changing needs and challenges. 31stly, remember to document all electrical work and modifications performed in the data center to maintain an accurate record of the power distribution system. 32ndly, ensure that all electrical contractors and technicians working in the data center are properly licensed and insured. 33rdly, use color-coded wiring and labeling to easily identify different branch circuits and power feeds. 34thly, implement a lockout-tagout, or LOTO, procedure to safely energize equipment before performing maintenance or repairs. 35thly, provide adequate lighting in electrical rooms and panel board areas to facilitate safe and efficient work. 36thly, use thermal imaging to identify hotspots and potential problems in electrical equipment. 37thly, consider using uninterruptible power supplies or UPSs to provide backup power in the event of a power outage and ensure continuous operation of critical equipment. 38thly, implement a system for managing and disposing of electronic waste in an environmentally responsible manner. 39thly, use cable management techniques to keep wiring organized and prevent accidental disconnections. 40thly, provide clear and concise instructions for operating and maintaining electrical equipment. 41stly, conduct regular safety training for data center personnel to prevent accidents and injuries. 42ndly, establish a process for reporting and investigating electrical incidents to identify root causes and prevent recurrence. 43rdly, use appropriate personal protective equipment, or PPE, when working with electrical equipment. 44thly, maintain a clean and organized work environment to prevent hazards and improve efficiency. 45thly, implement a system for tracking and managing spare parts and supplies for electrical equipment. 46thly, conduct regular inspections of electrical equipment to identify and correct potential problems. 47thly, use appropriate tools and equipment for electrical work. 48thly, maintain a safe distance from energized electrical equipment. 49thly, follow all applicable safety regulations and procedures. 50thly, always be aware of the potential hazards associated with electrical work and take appropriate precautions. The concept of oversubscription, particularly in data centers, is not just a matter of electrical calculations. It's a carefully orchestrated balance between theoretical capacity, real-world usage, and risk management. It is vital to continuously analyze the power consumption patterns and adjust the oversubscription strategy to match the evolving demands of the data center. By integrating these best practices, a data center can not only comply with the NEC guidelines but also optimize its power usage, enhance system reliability, and reduce operational costs. The key is proactive management, informed decision-making, and a commitment to maintaining a safe and efficient electrical environment.